We were recording. So, all right. So welcome everybody. Welcome to probably our fifth or fourth TWed of the fall term. I should let you know that we have one more TWed, which is next week, which Neha will be presenting. Then there's an R Pirates, I think, after the holiday break, and then it's the end of term TWed lightning talks, which you will be pelted with information about over the next couple weeks. A little bit of logistics. We are recording tonight's talk. We're not recording with video because we're still working through how to replace our video and screen share thing. We are recording the screen share and recording Jim's audio and the audio in the room. But unfortunately, we're not able to do that multiplex video and screen share that we did with Google Hangouts. We haven't figured out a replacement for Google Hangouts, and WebEx doesn't do it. Tonight, we're welcoming Jim to the podium, Jim McCusker, who's going to enlighten us on OWL and future of computability and all sorts of great stuff, and I won't destroy it by an introduction. So without further ado, thank you very much, Jim.
So we're looking at OWL at the Crossroads. So part of this is that OWL is actually a really interesting intersection of set theory, graph theory, logic, and computability, but also it's at a crossroads because there's a lot of interesting things happening in graph learning, in other areas, in reasoning that really OWL is both well positioned to take advantage of, but also we are well positioned as researchers to kind of set the research agenda for it. So before I really kind of get into this interesting stuff, make sure this works. There we go. So what? Yeah. So what's OWL again? Anyway, so OWL is the web ontology language, as spelled by Owl from Winnie the Pooh, who spells his name WOL. The fact that it's the web ontology language instead of the ontology web language or whatever. The joke is that the web ontology, so the acronym is the only thing that's inconsistent about OWL. I don't know if that came first or if they backed into that or if they had any they backed into it. Yeah, that's so. And then the thing with Owl from Winnie the Pooh, again, I don't know if they even were aware of it at the time or not.
I don't think that came up.
But okay. So anyway, from the actual OWL primer, web ontology language is an ontology language for the semantic web with formally defined meaning. So this is actually really important. OWL 2 ontologies provide classes, properties, individuals, and data values that are stored as semantic web documents. So these all actually kind of pile on top of each other to make some really interesting properties of OWL as a knowledge representation. A lot of us are already familiar with the idea that OWL lets you describe data and lets you describe how that data is shaped, or even talk about relationships between things and doing conceptual modeling and things like this. That's all true, but these are kind of some additional things to think about as you're creating OWL ontologies, as you're thinking about ways in which you can take advantage of OWL as a knowledge representation. So OWL is actually at the intersection of, as I said, logic, set theory, computability, graph theory, and semiotics. And it's the fact that these all overlap and they're all true at the same time creates some really interesting opportunities for us. So So I'm just going to kind of go through those, and then I'm going to talk a little bit more loosely about kind of the consequences of that. So the first thing is that OWL is an implementation of description logics. That's really what it is, and that's why Deborah has anything to do with it and to begin with, because that was her thing, was description logics. Description logics. So normally we might think of person, subclass of agent. This is actually the notation that you would see in DL. This square subset of. And the other thing is that because it's in description logics and because it's grounded in logic as a whole, there's actually a formal predicate logic interpretation for this statement, which is for all x, if person x, then agent x. And you see that also in things like the standard Socrates is a man, all men are mortal, therefore Socrates is mortal. You can actually express this, you can express that syllogism example as predicate logic, and also because of the way OWL's put together, you can actually express it in OWL, and you can have Socrates be an instance. It's a type, has type of man is subclass of mortal, therefore Socrates is also an instance of mortal. DL has other properties. In it, you have existential and universal quantifiers. Those are, when you actually see those in OWL, you see it as the sum or only. There's negation, intersection, so forth and so on. And that also has, each of those actually has a first order predicate logic interpretation. And actually, when you look at the OWL entailment regimes, you see this first order predicate logic as examples of how how OWL is interpreted. But you actually also see second order predicate logic. So the fact that there's an entity here and activity, those actually get replaced with their own variables in the logic. So those variables get replaced to become these interpretations that actually get run on in the ontology. So logic is really at the foundation of OWL, and it's in some ways kind of the place where it's been kind of most formally treated and where it's best understood. It's the way that that kind of the basis for how reasoners work, for how we understand how to interpret an ontology, and so on. Because of this, we can actually figure out what the decidability is, the computability is for a given piece of OWL. So you've probably heard us throw around terms like DL, OWL full, QL, RL, EL, and those are all different subsets of OWL. So OWL full is basically all possible statements that you can make using the OWL ontology. OWL full plus RDFS actually is a little bit bigger than this, but it's also undecidable. So you'll notice that kind of pokes out there. OWL DL is in DL. DL as a whole is decidable. And then these kind of these profiles are in polynomial space. In some of these, they're polynomial time. In other places, they're actually, I think they're p-space. Sometimes they're polynomial relative to the number of rules or relative to the number of concepts in the graph. But basically, the reasoning regimes around these subsets and around OWL as a whole has been very well has been analyzed to death. Really, I'm not sure of. I mean, generally, we're looking at more and more things we can kind of sneak in under DL, maybe, or maybe there's something that's not in DL, but it's also decidable. And then, so there's some research around trying to include things in maybe either in DL or in the decidable space. And actually, you look at things like OWL2 punning, where they said, oh, well, if we slice through the entailment regime this way, basically anything in the T box can't give you something in the A box about those two, about the same entity. That takes some interesting things you could say out of OWL full and puts them into OWL DL, but it's a trick basically, which is a neat trick, but it's a trick.
Are you going to expand UL, RL, EL?
I can. Sorry, good.
So in this diagram, and as you were explaining, so OWL, QL, RL, and EL, they can all be solved in polynomial time. But
Right, for certain things.
But OWL DL might take NP time.
Yes. Yeah. In fact, it can be NPX time.
Okay. And OWL full is not fully decidable, so it might take, like, it's a complex one, it can be NP hard or something that you can think of.
Right. Right. It's actually even not NP hard. It can be undecided. It's undecidable.
Okay.
So you don't know if it's going to halt.
So, how different is DL from propositional logic and first order logic and second order predicate logic?
DL is a subset of first order and second order predicate logic. So second order predicate logic is a superset of first order, adding a new variable for the actual predicate itself. DL is a subset of first order predicate logic that basically only allows certain formulations of those rules to exist. So if you look here, so basically there's this full interpretation in here. When I took first order predicate logic, we did some crazy stuff with that, right? Most of that's not allowed in DL. And so usually when I'm thinking about, if I'm making some sort of complicated restriction, sometimes I try to think about what's the first order predicate logic version of that I'd be thinking of in order to kind of wrap my head around what I'm trying to do. In DL, yeah, most of the stuff that you might be able to do in there, like the idea of having, basically even if or if and only if, and nesting them and doing crazy stuff with conditional, existential, and all that stuff. Most of that's not possible. And then most of the entailment that occurs in DL is syllogism specifically, as opposed to any of the other reformulations you might have. And
I was going to add some perspective.
yeah, go ahead. That's perfect.
So description logics, way back before they were actually called description logics, started basically to try to make the semantics clear to semantic networks. So they didn't then have this focus on computational efficiency. But by the time they ended up being called description logics, and actually by the time they were called terminological logics, they had different names throughout history. The theoreticians have kind of glommed up the community and kind of took enough control and influence to say, we're choosing constructors that can go into these languages for which we can have efficient processing. And so that's historically influenced description logic since the late 80s.
And actually, there's one other thing here that's actually important to think about as you're designing an ontology as well. So OWL is a meta ontology, right? You've got predicates and you've got classes, and they describe other predicates and classes. As they did this, and in some ways this was, it has a very long lineage, so it definitely has a lot of advantage over some of the short-term projects, relatively speaking, we have here. We don't have any projects that last 30, 40, 50 years.
Line agent's been around since the 80s.
Well, we don't have many projects. But so, one thing that OWL really kind of has going for it is its compositionality. And a lot of it comes out of the fact that it is a language that was designed to be a general purpose language for describing knowledge. And so it's very compositional, and we're thinking of things to do with it all the time that the people who originally envisioned OWL probably are spinning in their graves about, but it works, and we get it to work, and it's actually kind of cool. Like doing policy evaluation using OWL plus prov and all that sort of stuff. Or reasoning over individuals that was not envisioned as part of DL even originally. But if you can think compositionally about your ontologies as you're developing them, you can actually have some of those same properties in your ontologies as you would in OWL. And that makes what you're letting other people describe just as compositional, just as creative and interesting and long-lived as something like OWL itself. So that's actually something to take, I think, to take inspiration from in the design of OWL, is how reusable and extensible it is. And really, when we're thinking about trying to build long-lived knowledge systems, we want our vocabularies to have that durability and robustness. Okay, so also OWL classes are sets too. So basically, set theory is an important part of the semantics of OWL. When you define a class, it's a bunch of things that meet some criteria. And that criteria can be formally defined if you have property restrictions. It can be informally defined if it's written out in a definition, or it can be whatever I say it is, and just you do it by naming entities into that set. But no matter which way you're doing it, it's a set of things. And to some degree, this is actually a place where sometimes there's not necessarily difference of opinion, but a difference of interpretation, where you might have ontologies that are maybe topic hierarchies, or might be conceptual hierarchies, where you're not really thinking about the set theoretic aspects of the classes that you're creating. But they're still there. And so usually if I'm critiquing an ontology and I see it and I look at something and it doesn't seem right to me, the first thing I ask myself is, well, what would be an instance of this? So if you have like a top level, you might have in your ontology, you might have things like concepts. And then you might have under it, you might have maybe your top level classes, and that's helpful for gathering things up, which is great for that, except that what's an instance of concepts? Is it anything a concept, or are the subclasses the concepts? And so you have to sometimes think about whether or not you're thinking of this set theoretically or conceptually. You can do both, but you have to keep both of those interpretations in mind.
Do you have to? I mean, so
do you have to?
I mean, so this is. So I think it's possible to create a particular ontology that it may be simplistically conceived and it's capturing a hierarchy.
Yep.
But it might not be very useful for certain other for applications. Yeah.
Right.
And,
so it might not.
Is it not necessarily? If it wasn't intended to do that.
When I'm feeling pedantic, which is most days, I would say no.
It's Wednesday.
It shouldn't be.
Pedantic.
Yeah. I would usually say no. It should. You should use something like SCOS to represent those. And I've had arguments people in the biomedical field about certain ontologies and their use of OWL to represent conceptual hierarchies.
So-
they're still there. So,
I guess what in the
but this interpretation is still true. No matter,
I guess my view of it is, from what I've learned over hanging around with people like Deb and you and stuff, is you might not know what you needed to do.
Yeah.
Right.
Yeah.
That's really it. So you.
Well, yeah, and so a lot of this kind of implicit understanding of how these, how to interpret a lot of the things in semantic web. I review a whole bunch of papers where people do not really have that interpretation in their head, and I mean they're outsiders, and we should be welcoming them in. But at the same time, it's a little weird that you can have so many different interpretations of the same conceptual structure and not have it be apparent to people coming in that there's actually something very formal and very specific in mind. When you're talking about a class, it's a group of things, it's a set, and that's actually part of the formal semantics of that of the what we're talking about there.
So what you're saying is there is room for strict formalism. It's not just art, or sometimes sometimes art has nothing to do with it.
Yeah, exactly. And like a sonnet, if there's room for art within structure, and if you obey, so you can have a bad sonnet that follows the structure, but you can also have something that's almost a sonnet but isn't, but is really good. It does it reflect badly on either sonnets, the forms of sonnet, or even on that poem? Not necessarily, but it fails to be a sonnet, even if it's still great poetry.
But if you're not going to have the logical underpinning, so like if you want exceptions all over the place, shouldn't be using description logics.
Mm-hmm.
Right, exactly. Okay, so I'm not going to go, I mean, we've all seen Venn diagrams before. But actually, one other thing, though, is this notation of, so this is actually an alternate notation for what I had here. So this is a predicate logic notation for membership of if you're person X, then agent X, right? That's predicate logic. There's nothing specific about first order predicate logic and using unary predicate to say that this is a set thing. It's just, in some ways, it's just symbol manipulation. So you have a unary predicate person, and it's got an X is that. Here, we're actually saying mathematically that X is in the set of person. And if, for all X, if X is in the set of person, then X is in the set of agents. That's actually the set theoretic statement that you would make about class membership and class subsumption. Similarly, in DL and also in OWL, you can have intersections, unions, negation, and all of that stuff translates over to set theory as well. Right, and then so all of this kind of comes out of DL, description logics, and the way that description logics have been used in OWL. One thing that has been really interesting about as an implementation of description logics is the fact that it's also interpretable as a graph. It's interpretable as a graph, but it's also interpretable because so been represented in RDF, it's interpretable in a graph with specific features to it. So you can actually describe your data the same way that you describe your description of your data. So if you have a, if you have these definitions for different classes and for properties and other things, you're representing them in RDF usually. And at the same time, you're also representing the data itself in RDF, which sometimes we kind of don't appreciate as much as we could. And if you look at things like JSON schema and kind of the struggle that they have to actually, and Open API and a lot of other systems where they're actually trying to describe their metadata the same way that they're describing their data, they have a lot of trouble with that. And we've actually here with kind of cracked open a big nut in being able to inspect and describe our data and metadata in the same language. Because what it means is that there's no bottom to this rabbit hole. We can add things like provenance in. We can add meta information about these classes, and because the representation itself is extensible, the representation for the metadata is also extensible. We can add annotations and other interesting facts about our metadata to that graph as well. We can say why we think that father has a particular definition and where we got it from.
Is that the plain node where we are saying that father is equal?
Yeah, this is a blank node in the. So this is usually. This is a simplification because this is actually an RDF list. But this is the blank node that would be internal. And yeah, again, these are just kind of basic examples for that. The other important and interesting thing.
Wait, before you
Sorry.
continue.
Yeah.
So that one in the OWL intersection of the RDF list, what do you mean by that?
So when you actually have the range on intersection of union of, all different from a couple others have those all have the range of RDF list. So you would have the RDF. So the intersection of to another blank node, there would be a RDF first to parent, and then RDF rest to another blank node, which have RDF first to main, which have another to RDF nil. Yeah.
I actually have a question about verifying the decidability of something that you, sometimes when I write intersection of and etc. Syntactically it's fine. I use a total validator and it works. But then I don't know if it's actually in the decidable space. And
Yeah.
do we need to run a listener at that point?
Well, so generally, anything that you express in OWL that does not cross the boundary, so there's specific boundaries in OWL, like for instance, if you can't write OWL restrictions about the properties that are used in OWL, for instance. You can't say that a OWL class has min1 RDFS range, that sort of thing. You can't do that. You can't do stuff like that. Generally, that's why punning is in place. And so now, anytime you might come close to crossing that line, the punning will segment your inferences for you, so that anything that you say about the node as a class is, you can't make any conclusions about the node as a individual at the same time. So you can say things about it as an individual, and you can make conclusions about those statements, but you can't take into account any of the statements about it that you would talk about it as the OWL class. And so generally, what that comes down to is the RDFS properties and the OWL properties. So those all count for classes and properties. They don't count for individuals, except for RDFS label and comment and so
So kind
forth.
of follow-up question on that. Is there any cheat sheet that you refer to saying that this thing is allowed, this is not allowed?
So there's the OWL2 profiles. We'll have for QL, EL, and RL. We'll have descriptions of what's allowed in each. Beyond that, if you design an ontology and you load it into Protege, it will give you the alphabet soup for that ontology. It'll tell you kind of what the DL complexity is for it. It's usually and actually I don't have a slide in here about it, but basically there's a DL complexity navigator. If you literally Google that DL complexity navigator, you'll come to a web page that if you plug in those letters, it will then tell you what the complexity is for that whatever subset you're using.
Yeah, and there used to be co-ode or whatever that just told you
Oh, yeah.
species. I was just
Well,
looking
yeah.
it up. I'm
Well,
not sure it's
Protege
still
will
there.
tell you the species. It's very specific. It won't tell you the genus or order,
Okay. Okay.
as it were.
It went in 2004. That I was just looking.
Yeah, and I mean that's a useful tool that probably would get a ISWIC paper, is to kind of pull that together with all the modern OWL2 stuff. Just
Yeah.
look at the ontology, figure out what profile it's in, what species, and then like is it in showing? Is it OWL1, OWL light, all those. So okay. Anything else on ontologies and graphs? You'll notice I have a lot fewer slides than we have.
You have as many slides as you're talking.
Exactly. And so I knew we were going to spend a lot of time on each one.
You get great photos in your slides.
Yeah, and really, I did enjoy finding owl pictures today. Okay, so finally. OWL as a whole is because it's represented in RDF, it actually has some very interesting semiotic properties. So semiotics, if you're not familiar with this, is the study of symbols and their relationship to the world. So how do humans use symbols? How do they use them to think? How do they use them in social systems? And how does that actually relate to the things that they denote? And so here, actually I didn't label these edges, but that's okay. Basically, there's the symbol. So OWL is a symbol for that we use to talk about things. There's a thought that when we think about owls, we get a certain thought in our head, and that's that's a pattern of activation in our neurons. Then there's the actual thing in the world, the actual owl. And so we say that and so basically there's a link between the entity in the world and the symbol, and it's mediated by the way we think about it. The interest and the symbol kind of has this indirect link to the referent, because the symbol refers to a thing via that thought, and we kind of, as humans, we mediate that connection. The interesting thing about the semantic web is that it actually provides a way to, it provides this shortcut in an interesting and weird way, because we can actually say that every URI denotes or refers to a single thing in the world. And every time we use that URI, we're always talking about the same thing. We're actually creating a social system that helps us mediate this process. Because if I say owl, we talk about the bird, I could be talking about the ontology language, I could be talking about the examinations in Harry Potter, yeah. You know, it could mean a whole bunch of things, and you don't know what I'm talking about until I've given you more context for it. Even within the context of this talk, I'm using actual owls enough where it can be a little confusing. And so the word owl is insufficient to link us to a thing, an actual thing in the world. With RDF graphs, we actually have a universal identifier. Of course, this still doesn't tell us. This actually probably is actually the URI for the species, for the actual owls. But this refers to one and only thing, and that's the class of birds that are owls. This is still a little misleading because it's not actually this particular owl. I don't have an identifier for this owl. I could probably make one up if I wanted to, but the cool thing about the semantic web is that this shortcut, the fact that we all know that we're always talking about the same thing when we use the same symbol, is, in a sense, it kind of takes the need for this out of the picture. We don't need to link back to the same referent if we always know the same identifiers is in place. Because we're basically, so rather than disambiguating by saying, oh, he meant ontologies, okay. And because I've given you additional context to resolve that, because I'm giving you URI, there's no extra work to do there. It's just there and ready to be used. And so as a result, this can be, in some ways, you can have a computer do this piece, the thought part, without it even having this link here, right? They don't know what owls look like or what they do, or, I mean, they just know, they just have this symbol. So it's as if you were, you know, let's say we start talking to Martians and we think owls are so amazing we have to start describing them. The only point of reference they have is everything else we've described to them. And there's not, they've no actual, let's say they don't have any images of owls. They might have some text that we gave them, but they don't really even understand English necessarily. But they know every time we use this URI, we're always talking about the same thing. So computers are in that same position, right? They don't know what we're saying, really. They don't understand images. They haven't seen the world the way we have. But they can still process knowledge in a structured way about these things because they know when we mean the same thing. And so that's really kind of one of the cheap tricks of the semantic web that is actually really valuable. I've been chasing universal identifiers since I started working with databases. It's just, annoyed that I had to do it because URIs are long and kind of annoying. But then I realized that it was actually what I'd been looking for the whole time, and it was pretty cool. And so if you think about the way that all fits together, this is all true at the same time, right? So we have universal identifiers for things that are describable using graphs, where you actually have this full open-ended structure, lets you describe data and metadata at the same time. Using those things are described using set theory, and it has formal semantics both in set theory, ability to describe these things. You have the ability to formally define kind of the relationships between things and encode knowledge, and really kind of get this whole thing all together. This is all true at once. And so we have the ability to really play with that space and think about, well, what does all that mean when we're doing research in this stuff? What does it mean that we can actually think about have such a consistent system of semiotics and logic at the same time? What is the actual intersection of set theory and graph theory? Beyond, okay, well, we're describing these graphs. Well, what are some interesting advanced graph theory we could be thinking about that we can apply to set theory in a way that might actually give us some interesting insights into ontologies beyond just basic reasoning? These are all open questions, right? We can basically take a dart and hit any of these things on the outside and investigate that as a potential feature of OWL, that there's some considerations or consequences there that we can be thinking about and say, hey, this is an interesting area. Let's figure out what that means. So I'm going to give a quick example of that. Two quick examples. It's not an owl. It's a lemur.
Yeah.
What's lemur stand?
I don't know.
Logic enabled.
Yeah, go for it.
I'll get back to you on that.
Okay, so let's think a bit about graph learning, right? So there's a whole bunch of graph learning algorithms out there, graph embeddings, trying to predict node links and so forth, and possibly even encoding interesting properties into the embedding space, like king minus monarch equals man. You can actually do that in some embedding spaces, which is really neat. So that's fine and all, and there's some interesting, so that's actually trying to, there's some interesting graph theory going on there. But there's an interesting consequence of graph learning and machine learning in general that I think is worth exploring. And that's the fact that we still have the semiotic triangle, right? And so some people in graph learning, they're like, well, let's just throw out the symbolic graph and just work with the embeddings, and we can do all sorts of crazy stuff in there, and it's really neat and interesting. And what else do we need? We've already got that. You'll be missing out on this, right? And so what does this have to do with graph learning and embeddings? Well, I was just saying that this link is missing, right, in the semantic web. The link between thought and entity. Normally, what we do when we think of a thing is we'll either, it'll be activated by the symbol. We'll say owl, and boom, you've got an image of an owl in your head. That image of an owl in your head, what is it? It's a neural embedding. It's a pattern of neural activation in your brain. You represent it numerically, it doesn't have to be. But if a computer were to do the same thing, it would look a lot like an embedding. Similarly, if you have image recognition software, and it's able to look at this image and think, owl. Owl. Gives you the label owl. That's great, but you don't have the link back to what you know about owls. And so what does that mean for graph learning and for image recognition? Well, how many of you have seen a magpie before? Like, okay, so some of you have.
I've been accused of being a magpie.
I would back that up. I encountered
like shiny things.
in New Zealand. In New Zealand, I encountered a whole lot of magpies. They're really interesting birds, both visually and the way they behave. But even if you've never seen a picture of one, I could describe it to you in words. I I can say it's got white bands on its wings, really thick white bands, and it's got a white on its back. It's big like a crow. It's related to a crow, and it has a really, really weird call. All those things. That's all you need to know. The next time you go out, if you were to visit New Zealand or Australia or Southeast Asia,
Bristol, UK.
or anywhere where they've got some, you'll recognize it. You'll know when you see one, even though you've never seen one before. The computer can't do that yet. But that's because it's working with, so we have systems that work with symbols, and they're able to operate those symbols but not really understand what they're talking about. We have systems that are able to recognize things but not really have any understanding of what it's seeing. So you can do things like spoof. You can throw a little bit of static over a picture of a cat and you don't think it's a bagel. But the reason why it thinks it's a bagel is because it's not looking at it the way we are. We're looking at it with this mix of symbolic reasoning and visual reasoning, visual recognition. And these two are intertwined in our brains. It's not one or the other. They're very related to each other and very reliant on each other. Even to the point where if you're reasoning about certain kinds of birds, you've got pictures of birds running through your head as you do it. It's just, in most cases, it's automatic. And you don't get that without having the symbol and the embedding together. And so that's one thing that I think is really interesting that I want to pursue. And then kind of on that note, the other piece of that is that there's been a lot of interest around causal reasoning and kind of trying to build up almost a new branch of statistics that works a little bit more like how we actually do reasoning about the world and about cause and effect. To some degree, and the thing is that there's a lot of that is actually based on graphs, and a lot of it's based on the idea that we have a certain number of assumptions that we can make, a certain amount of embedded knowledge about the world that we are pulling in when we do this sort of reasoning. And the fact that you have that, but you don't have they don't really have kind of this big knowledge base for it. They don't have millions or billions of facts accumulated to work on these causal graphs. There's also an opportunity there to really try to figure out what might be, figure out how you can together and do some real insight from just the basic understanding that we have in our systems. Yeah.
So, I don't know how deductive reasoning is actually different from causal reasoning, because you're kind of reduce the reason as to why something got to a particular point, right?
No, because what's going on is that in causal reasoning, in deductive reasoning, all we know is that if this thing is true, then this other thing is true. So we have basically the if and then, right? There's nothing in there. There's nothing in this that says why we think it's an activity. What makes this an activity? All we're saying is we know how to recognize it as an activity or an entity. Yeah, sorry, as an entity.
Compositional relationship in the ontology tell you what an activity looks like and what it is?
Well, so first off, so causal reasoning also has isn't really so much about trying to get so it's actually more probabilistic than that. So you actually get the probability that certain events caused other events based on the model is being used, the links between them have linear or nonlinear functions associated with them, so that as the probability of one event happening occurs, that's actually gets translated through the graph to the final thing. And so you get both a prediction as to if you don't know if something is going to occur, you get the probability that's going to occur based on these conditions, the probabilities associated with each one. But conversely, if you have the conclusion, if you know an event occurred, you can go backwards and say, well, what's the probability that this thing was the reason? And so it's not a deduction in that sense, and it's not conclusive in the way deductive reasoning is. But even if you look at fuzzy logics, there's no guarantee of causality in those conclusions.
Tell me if this is a fair statement. In say you have a complex graph,
Mhm.
The relationship from one node to an adjacent node, you might call that a deductive. It's one hop. Whereas from one place in the graph to some other distant point of the graph, you can't necessarily deduce that. You do need a much more probabilistic thing because there's multiple paths that can be followed.
If you're talking about state transitions,
And
then
this
yeah,
is where causal reasoning would really come into play.
potentially, yeah. Well, it really depends on what you're describing with the graph. So if you're describing potentially conditions or events occurring, and the fact that one might drive another, then yeah.
You have an initiating event at some point, and ramifications cascade across the graph.
Yeah, that you often want something that's more like a causal graph. Because, I mean, really so if you're talking about kind of a standard knowledge graph, there are many different kinds of links in there. And it's not necessarily, you can't, propagating something across that representation doesn't always mean that you're thinking causally about something. You might say that a particular statement or group of statements might be a cause for another group of statements or statements. But you need to establish that sort of relationship.
You have to express those, that's explicit.
Yeah, exactly.
That
So
has
a
to
deductive rule might list out those initial conditions and then say, here's some other set. So if you have 5 statements in a rule, if you see those statements, then these other 3 statements. That's a rule. That's a deductive rule, and you can add that and have it be incredibly distant on the graph. As long as the patterns match, then it doesn't matter. But with causal reasoning, it's more about trying to say, hey, here's a particular type of edge in the graph. X causes Y. And it could be a simplistic edge, it could be a complex edge, depending on how you represent it. But the fact that you see an instance of X is a indicator, a probability that you'll see instance Y, just because of that link. And so some of that is often you have a set of assumptions to start with, where you think, here's some associations that you've seen, or here's some background knowledge about other connections in the graph. And then causal reasoning and causal statistics lets you basically analyze that and look for assumptions and control across your different observations. It's a way of interpreting data relative to this to a set of causal interrelationships to actually do that. But the cool thing about, to bring it back to knowledge graphs and OWL, is that right now causal reasoning doesn't. You've got your causal graph, and that's a graph, and it's pretty familiar with what we do. And then there's your table of data, right? And you have to interpret that data in a way to align it with your graph. And you need to know that this column corresponds to this node, and this other column corresponds to this node. And so we have the opportunity in our system, in the semantic web, to actually say, well, we've got these linked already, and we can actually go out and discover cases that look like this causal graph and might contradict or confirm what we're seeing in it, and just have it happen as part of kind of a larger reasoning system. It doesn't need to be kind of a one-off, here's the causal graph, here's the data we've applied to it. We can actually go discover the data.
Causality or reduction, expressive causality.
In the sense that if you have, the conclusion might be a prediction with a certain level of confidence, then yeah, or an explanation. So like causal reasoning can do both deductive in the sense of predictive reasoning, but it can also do explanatory reasoning. So it can say, we see this event, and so here are the probable causes of that event, because we see these other conditions.
So, how do you assign probabilities to that?
Well, that's a good question. I mean, basically there's a whole set of, it's a whole set of whole branch of statistics that I can't explain.
Yes. It's Judeo-Pearl, right?
Yeah, Judeo-Pearl. So if you're interested in learning more about that, there's a book called The Book of Why, which kind of gives the layman's introduction to it. There's also
Why is it WHY?
Yeah, WHY. And then there's also I found a review he wrote that's more rigorous and more mathematical if you're interested.
And there's 10 papers out there you can find that try to explain either thing that he wrote.
Yeah, exactly.
He was a mathematician.
But if you just
He's a computer scientist.
Yeah, he's a Turing winner for
Bayes nets. He invented Bayes nets.
Yeah.
And then he was kind of disappointed in what you could do with them and realized that.
Yeah, actually, he had like this huge guilt. He's like,
Yeah.
Invented Bayes nets, won Turing Award for that. And it's like this tremendous. Like,
wasn't what he hoped. Yeah.
It's not as simple as that, Pearl.
Yeah.
Just Google and do calculus. That's awesome.
Yeah. Yeah. DO.
So here's a question that I've been wanting to ask for 10 years around here. Actually, 14 years.
Okay.
So let's say, so you've got things out there, like lemurs or owls.
Yep.
Okay. But you've just got entities that are your eyes. But you can also have functions, which are URIs. Like think of them as endpoints or service points.
Okay.
And I can have F, and I can have G.
Mm-hmm.
Okay. And I've got X. I can have F of X. X is a specific thing. And X is, F is, G is. For all the, there's a specific meaning of this.
Right.
And I can have, in function speak, I've got F of X, I've got G of X, I've got F of G of X.
Mm-hmm.
Each one of those, by functional programming, say, that's equivalent to a unique identifier. Okay?
Mm-hmm.
F of X in like Haskell that's an identifier.
Yeah.
You can imagine a web-based system where I could go to X or I could go to F of X, and that's always by our rules of URIs.
Right.
That gives me the same thing, conceptually, or F of G of X, whatever.
What's the output of F and what's the output of G?
Yeah, is this even allowed in
No, it isn't.
Actually, well, this is kind of the question. Okay,
No, it
You know,
isn't.
but from a web, no, well, I'm wondering what
It
is.
isn't allowed, why not?
Well, no, actually, that's what I'm getting to. It's what I'm trying to do. What I'm trying to understand is, because from a web standpoint, what I'm talking about is completely by the rules. Okay, because I've built systems like
Right, so you pass,
where
pass the output, so you have X, which is a,
yeah, whatever. It could be an image.
And you
It could
pass
be an
a-
image
yeah.
URL.
And
And f of x, f is a transformation point. F of x is a purple version of the owl.
So are you basically saying that any C++ statement can be thought of as a URL?
Get away from me, old man. I'm not talking about C++ at all.
I'm just
It's you that are having these introverted thoughts. What I'm saying is, I can have x, the
Yeah.
URI. I can have f of x as a URI. I can have f of g of x, which is the upside down purple version of the cat.
right.
Okay, those are all legitimate URIs, and from a URI standpoint, those are.
Yeah, and if you encode, well, no.
What I'm trying to understand is f is making things purple. Okay, f is the function that makes things purple.
Okay.
Okay, and I'm not trying to be facetious. I'm trying to
Right.
there's a thing that gnaws at me forever where you combine like the functional aspect, functional programming cross. What I'm asking for is functional programming cross semantics. Where,
Right.
okay, how do you represent in web reality space? F of x is making the cat purple. Okay, what is and from an ontology standpoint, how would I reconcile all of this?
Well, so I mean,
Right.
Well, yeah, so F and G would be activities, and you
Right.
have
Yeah.
used X, and then G used the output of F.
Crowd space. Right?
Yeah.
Yeah.
So yeah, those F and G would be subclasses of activity.
Mhm.
You would that's how you would encode that. That wouldn't be the same thing as running it, of course.
Yeah, and we could have done it, so we have a functional programming group right next to the description logic programming group at Bell Labs. So, you could do some kind of connection. So like classic, you could have a rule and then you could run it and make things purple.
Right.
So an early
Right.
description
Well,
logic.
And the main thing though within the ontology space is what statements are you making about F of X?
So what I'm saying, f of x is the purple cat. It's a
purple cat, or it's a the process of purpling a cat.
no
So,
f. Okay,
so X
f
is the cat.
function. I mean, I should say maybe I misspoke. F of x is the purpleator. Yes, that's very good. F of x is the purpleator, and then A, or let's say C.
Okay.
C, the C is the cat. Okay,
Right.
so F of C is that cat, that instance of that cat purpleized.
Well,
And it will always be. And it either whether it runs it every time I ask for it or caches it,
What would you
it's the same purple cat.
So, sure, but what's the relationship between C and F of C?
What are you making purple, the inside or the outside?
No. C is
No, but real-
C is a cat.
No, but what's the relation? What is the relationship between C and F of C? That's what ontologies are trying to express. And so, yes, you can express operations using URLs. You can do all sorts of things with URLs, but it's not the same thing as saying, hey, here's
C
this.
has no relation until after I do it.
Right. And so you
beforehand,
wouldn't
C is a
express it
cat.
now.
And afterwards, C was the thing that was made purple. By
Yeah.
F.
So you wouldn't. So I mean, in the semantic web, URIs are also opaque. So
Yeah.
there's if you
Yeah.
have if you're composing if you had this system of expressing composite URIs like you're talking about, or functional URIs, as far as OWL goes, there's just more URIs. The process of submitting and getting that data back wouldn't have any relationship to the semantic web necessarily. unless you had a way of expressing those relationships.
I think it comes down to where, yeah, so I've got these two spaces where, so I construct, so I've got my C for my cat, and I've got my F, which is the function which purpleizes it. And then by some means, I put those, I get a new URI, and then essentially the process of composing that says, oh, by the way, this is how we are going to describe this with prof.
Yeah.
You know, in the same way
Exactly.
we do anything.
Yeah, you would say, yeah, you would say,
There's a work, yeah, something, and it doesn't necessarily have to. I mean, we're implying that it executes, but once we've done it, it's just a block.
But John, isn't this all in the apex of the triangle? In your mind, like you say, this is the thing that makes cats purple. In our minds, we know immediately what you're talking about. So there's got to be a way.
That's really scary.
I mean, you can envision. He's got a crown on his chin.
he was just telling me he was messing around with image magic. So now I know what he was doing. With image magic.
We should shut her down. We should shut him down. So let's thank Jim. Thank you very much.
And thank you for stretching this out to an hour.
Yeah, and I thought you were gonna end up doing